I'm going to take a look at a few more examples that are going to, again, connect all these pieces of these areas, anti-differentiation, and the fundamental theorem of calculus, part 1. So this first question, find the area bounded by the graph of y equals x plus sine x and the x-axis on the interval 0 to pi. So you could draw the picture of x plus sine x if you know what that looks like. You probably don't. We don't even need to know that. We just need to know, what is this even asking for? How do I find the area between a function and the x-axis? So what we should be thinking of is that we want a definite integral. So what this area is going to be the integral of x plus sine x. And we're doing this with respect to x. So we have our dx appear there. Now the bounds, we're going to find the starting point and the ending point. So our left interval is 0, or our left endpoint 0, our right endpoint is pi. And now we use the fundamental theorem of calculus. So we find what is the antiderivative of this. So we find the antiderivative of x, which we know is going to be x squared divided by 2. And the antiderivative of sine, that's going to be negative cosine. So we have negative cosine x, and this goes from 0 to pi. So remember, top goes in first, so I plug in the pi. So I have pi squared over 2 minus cosine of pi. And then I subtract off this whole expression when I plug in 0. 0 squared divided by 2 minus cosine of 0. Pi squared over 2 just stays pi squared over 2. Cosine of pi, well, if we remember our good old friend the unit circle, cosine is the x values. So at pi, that's an x value of negative 1. So I have a negative 1 here. Now on the inside, I have 0. Cosine of 0 we know is really a positive 1. So we have positive 1, so this becomes a negative 1. So flipping all of our signs, this becomes pi squared over 2 plus 2. So that is the area bounded by the graph of this. So if you were to actually sketch what this graph looks like, it is a weird looking graph that kind of looks like that. And so we have a very strange area that this allows us to now calculate fairly quickly. So that's another example I want to give. This can be a tricky example because you might be inclined to forget that you can't separate integrals when things are being multiplied. You can't just find the antiderivative of x and then each of these. You instead have to combine everything first. So make sure you combine things. So this would be the integral from 1 to 2 of 5x to the 4th minus x dx. Now, as long as nothing's being multiplied together except for constants, then we can now use our integral rules. So I add 1 to the power. So I have 5x to the 5th. I divide that by 5. I add 1 to the power, divide by that power, and I'm going from 1 to 2. So this is the same thing as x to the 5th minus x squared over 2 from 1 to 2. Top goes in first, plug this in, so I have 2 to the 5th minus 2 squared over 2 minus 1 to the 5th minus 1 squared over 2. 2 to the 5th is going to be 32 minus 2 squared over 2, that's going to be equal to 2. Minus a 1 minus 1 half. So this becomes a 30 minus 1 half. And so this one becomes 59 over 2. Notice I don't use decimals. Decimals we're going to try to avoid. We're going to get a lot of fractions appearing because every time you have to divide by the power, you're going to get fractions. So it's going to be in your best interest to keep fractions. Don't start trying to use decimals because the rounding errors will just start to accumulate. And so you will get fairly wrong answers a lot of the time if you start to round. So use exact fractions.